Yeah, so hi everyone. Thanks, Richard, David, for inviting me to this forum and giving this opportunity to present. So I'll do a quick presentation on how we tackle the model inference, in particular image generation at DataCrunch over the last few years, and a few steps along that journey. And also, I'm super happy to be interrupted. So if you have any questions during the course of my presentation, I'll be more than happy to answer them. So a few words about inference and DataCrunch. So I view it as, from my perspective, I'm the CTO at DataCrunch and I run the software development. So there's a lot of people working on both infrastructure and software. So I'll be trying to combine the story from different teams. And so that will be kind of my perspective in this presentation. So we are a Finnish AI cloud provider. We've been operating for around 5 years. We've been mostly bootstrapped. We raised our first round last autumn. What we do is we offer several different kind of configurations of compute for machine learning training, inference, experimentation, as well as general HPC use cases, which are, however, usually in the minority. So things like particle simulation, etc., are not like our primary kind of use case, but we can cater to that. So what we offer is clusters for training. So typically, this is multiple machines connected with InfiniBand fabric. We offer EC2 style cloud instances. So we have extremely easy to use cloud dashboard where people can just come and order a virtual machine instance running on Nordic clean energy in Finland and Iceland currently. We offer managed inference where people can come and bring their own container, fetch it from any registry that they might be using, either AWS or Docker Hub or GitHub, and then sort of we take care of scaling of that. And that's going to be one of the primary topics of what I'm going to be talking about today. And also we are working on several cool things, such as managed Kubernetes clusters, so that each customer would have a single tenant case with ability to auto-scale and plug in more GPU nodes, as well as things like more advanced networking, etc. So one way to think of us is like a thin layer of AWS or GCP or Azure focused on AI without kind of legacy cloud features. So we are kind of all in on AI, and we own our own hardware, and we develop our own software on top of that to be a full-fledged cloud provider. So that's about us. So without further ado, a bit of timeline. So we started meddling with inference already in 2021. That was prior to ChatGPT explosion. So we've been working with things like Bloom and GPT-2, etc., just playing around with these models, offering the API endpoints, running things like YOLO and other kind of image-related models. And as the industry matured and crystallized, we played around with doing kind of drag-and-drop multi-model inference pipelines where you can add multiple models in a row, feeding the output of one model to the next. As we see now, there's things like Comfy UI, which are leveraging that idea and taking it to the next level, while we ourselves pivoted more towards the lower level at the infrastructure level, where we would take care of optimized endpoints, running these endpoints quickly and sort of at kind of low cost. And finally, in 2024, we did serverless containers beta. But as we've been sort of handling these millions of requests per day, that gave us sufficient kind of knowledge and understanding how to productize that and build a general purpose feature where people would be able to bring their own Docker image with a container with their weights and sort of deploy that. And now we are working again on different managed compute options. So when thinking about inference or any kind of computer science program, there's a bunch of trade-offs. This is not an exhaustive list of trade-offs when thinking about what to optimize for, and the way you optimize it by adding more hardware or parallelizing or actually using cheaper hardware because you want to cut down your costs, etc. So latency versus throughput is one of the classical trade-offs, especially in LLM space, where you want to either with latency, you optimize the time to each token for every customer so that customers get the tokens faster, while throughput is the total amount of tokens that you can push through in 1 hour or 1 second or per unit of time. So then this is again time versus cost kind of trade-off is do you put in a really expensive top-of-the-line GPU and get your images generated in 1.5 seconds versus using an older generation and have 10 seconds per image. And then time versus accuracy is again one of the relevant trade-offs that I will briefly touch upon here. So things like quantization distillations will directly affect the accuracy, but by sacrificing some accuracy, you can gain time. These kind of trade-offs are not always, you cannot always make the trade-off, so sometimes you just need the high accuracy and are willing to basically throw more hardware at it to keep your time constant. So these can be chained. So in one after another, so you can cut down time by adding hardware and keeping accuracy constant. But these kind of define what kind of decisions the people who run these things in production, what kind of decisions they need to make. So when coming to inference at scale, one of the biggest things that we need to be mindful of is extreme jitteriness as well as cyclicity of the traffic patterns. One thing is when running kind of nightly batch inference jobs, you can kind of maintain and control the rate at which the requests are coming. So you can reserve a certain amount of EC2 instances in AWS and do your batch processing through 1 week or 1 night or whatever is the volume of your data. But when dealing with online queries with users, let's say in a certain time zone, so the blue chart here is basically showing a daily pattern of usage for some endpoint. These kind of loads are very hard to handle if you only have a fixed GPU allocation. GPUs are typically hard to come by at volume, and many businesses are forced to basically have a situation where all the black areas here is essentially idle GPUs. So a problem that we are tackling is to minimize this idleness and sort of average that idleness out across multiple customers. And as this traffic is extremely jittery and sort of unstable in its kind of amount, it cannot be solved without the queue. So an efficient queuing system and algorithms for handling the queue and sensitivity to sort of scaling up and down the infrastructure is quite important. So we built a quite standard queuing mechanism to handle this. So this is the rough diagram of our overall inference architecture as it stands right now. So for every customer endpoint, we will create multiple replicas of that container depending on the queue-based scaling settings. So let's say if you have 10 requests per queue and you have one request in queue per replica kind of setting, so that for every waiting request, there should be at least one replica on the other side ready to consume that request when it's done with its current work. So that would mean that you would have 10 replicas on the other side. So this is all handled automatically. We have a user interface for handling the timeouts for creating and destroying these replicas, as well as the max number and lowest number of static replicas if that's something that needs to be done. So the problems that we've been tackling and still working on, so minimizing the startup time for each replica, that's still very much work in progress. We have done quite a lot of work to make the individual replicas start faster, but there's also quite a lot of work to do. So this is kind of rough diagram of what we are doing with the queue-based scaling, and we added this kind of little widget to sort of hide the complexity of dealing with queues. So this kind of widget basically tells you that on the Lightning side, you will scale up as soon as you have even tiny fraction of requests in a queue, while on the orange side, it's more like a bad job mode, where you can let the queues fill up and the requests will be handled eventually. So this is more efficient on the use of hardware at the cost of, total, at the cost of latency. So this is kind of cost optimization measure on this side. So again, this kind of ties back to some of the trade-offs I was mentioning earlier. So this kind of ends the section on the architecture part of how we're doing the inference part. So next part, we'll talk a little bit about optimizations that we've been looking at. I will start by quickly going into the floating point formats and distillation, and well, actually quantization. I will not go into distillation, sorry. And also after that, I will discuss a little bit about how we use Torch compile to speed up inference time for image generation. So a very kind of rough picture of Torch compile. Maybe a show of hands. How many of you have used Torch compile for speeding up your models? All right, cool. So I'll sort of give a quick primer on what Torch compile is. So as the name mentions, it's a compiler for machine learning models, and what it does basically, it breaks down your code into components and then sees if those components can be merged into more efficient kind of chunks. So it breaks down what it is that you're doing and finds a more efficient order of operations. Typically, these are different types of matrix multiplications for different shapes of incoming matrices. You might be better off using specific implementation of matrix multiplication. So the full Torch compile stack consists of multiple steps. So the first step here is Dynamo. So what Dynamo does, it takes your Python code and converts it into a computation graph. So computation graph is just it's a directed graph of operations one after another, which can then be serialized and consumed by the GPU. And another important part to keep in mind here is Inductor. So Inductor actually takes in your computation graph, the structure of your code, and then optimizes that structure to run faster on the GPU hardware or the specific kind of hardware. You can have multiple targets. You can have CPU as a target. You can have various GPU architectures, not only NVIDIA, but others as well as targets for your Torch Inductor. So one of the key jobs of Torch Inductor is operator fusion. So assuming you have multiple small functions that do something to your input data, to your input tensors. Let's say you have you fetch two tensors from high bandwidth memory, so GPU memory. So memory here is GPU memory. So you fetch some data from memory, you perform a compute, and then you store it back to memory. That's a typical kind of, if you write your PyTorch kind of model, your forward pass, this is what will happen for every operation that you do. Let's say like it's NN linear, or some sort of matmul, or you do some normalization or something. You fetch the tensor from memory, you do your little line of Python code, and then you're going to send stuff back to memory. Or within that line of Python code, you might actually have multiple fetches and stores. For next operation, again, it's the same thing. Now, due to how the GPUs are architected and what the physical limitations of the high bandwidth memory, so-called GPU RAM or VRAM, the way it's structured, this is extremely slow versus the actual compute time. So doing these back and forth round trips is extremely expensive. And what Torch Compile does among one of its core functions is actually figures out which of these operations can be combined. Maybe in some cases, some of these intermediate outputs can even be recomputed instead of being fetched from memory. So what it does, it combines multiple of these operations into one, and thus saves the round trip time to memory, which is one of the longest taking operations. So if you look how much time is spent by GPU doing different things, oftentimes in unoptimized code, the longest time is actually spent by just fetching and storing stuff to memory. So we really don't want to go to memory almost ever. We want to keep everything in a tensor cores, in the compute part of the GPU, and thus the operator fusion performed by Torch Tensor can typically give very, very big improvements in performance. Few words about floating point numbers. So as people have been working on running machine learning models more efficiently in production, different types of smaller floating point formats and integer-based formats have been devised to kind of simplify, to make the memory requirements smaller on the one hand, but also make the forward and backward pass faster. And in particular, we have formats like FP8, which are now natively supported by accelerators like H100, H200, and beyond. And these can run essentially in parallel, kind of taking the space normally taken by the larger floating point formats like FP32. So that is much faster to perform those operations. Now, once you cut down the number of bits in your floating point representation, you necessarily lose accuracy. So if you naively you train your model, let's say in FP32, then you can probably, without loss of quality, go down to FP16 when you do inference. Now, if you naively go down to FP8, you might actually lose some quality and precision. And if you further lower the number of bits in your floating point representation, such as going to FP4, you potentially might start getting artifacts, considering the rest of your architecture descent. So you'll get higher error in general for your LLM or image generation or any other kind of model. Now, there seems to be a relationship between the number of parameter and kind of the precision. So here's there's a little kind of thinking nugget for the audience. So given you have a same memory usage by two different models, so 4 bits times 60 billion versus 8 bits times 30 billion. So 60 billion here is parameters, so number of floating point numbers in the model kind of states dictionary. So the question is, given you have two models, one model has lower precision parameters at 4 bits, but higher number of total parameters, versus another model which has 8-bit precision per parameter, but 1/2 of total parameter count. So it's a smaller model in terms of parameters, but higher precision per parameter. Which of these models will perform better? So maybe could I have a show of hands who thinks that the 4-bit 60 billion parameter model will work better? All right, so at least from on-screen audience, I see two people. Okay, and what about the 8-bit 30 billion model? Who thinks this one will work better? So 3, 4, and slightly more people think that this one will work better. So let's see what's the actual result from a recent paper. So well, it's not so recent anymore. So the result is from the end of 22 by Tim Detmers, who is one of the authors of QLoRa, of LoRa fame. So he's one of the main people in the low precision research. So he did actually run a same model architecture with different precision. So the orange line here with highest accuracy is actually a 4-bit model, while the 8-bit model with total, so this is total model bits. So these two on a vertical axis, you will have the same number of bits, but this model up here will have half less parameters than this one. So it seems that by increasing the number of parameters but decreasing the precision, you actually get higher accuracy. So you are welcome to check out the paper after the presentation. But at least on my side, my intuition is that the 4-bit 60 billion model performs better. Is that the model internally can make more choices. So you can think about every layer in a model is every transformation, every kind of linear algebra operation that the model runs through is a set of choices that the model can make. It's like, you know, given 20 questions, guess capital of which state I'm thinking of, these kind of decisions. So if you're given 60 choices versus 30 choices, your precision will be better, even though the granularity of every individual choice is smaller. So the total number of choices kind of determines the quality of the output and not the precision of each individual choice so much. So this, at least, is the kind of intuition that I'm having from this. And there's been also literature recently about convergence towards 1-bit precision. So what does that mean? That every weight is actually not a floating point number at all, but a kind of tanh kind of compatible integer, so between -1, 0, and 1. And what you can do then is actually skip multiplication completely. And multiplication is a much more expensive operation computationally than addition. So by going away from floating point calculus towards kind of Boolean logic, essentially, in how you handle your weights, a hypothesis would be that you can actually have extremely fast hardware computation, which is purely digital. So in some, not purely, like purely kind of logic based. So there's no kind of imprecision in the individual weight. So it's purely kind of decision matrix, and no probabilities kind of involved in that, encoded in the weights. So that's kind of interesting result. Again, we don't see that yet in practice, truly kind of Boolean based models outperforming. So, but that's maybe one thought to keep in mind. So yeah, having said that, we applied some of these findings in practice. Our goal was to take a Flux1 Dev image generation model, this happened last autumn, and make it run much faster. So what we did, we applied Torch compile, and we did it through multiple steps. So first, we started with 7 seconds in runtime. We start with naive Torch compile. It threw out some errors, and we fixed them. So the kind of errors that Torch compile might throw at the first run, it will detect some if-else statements. So these if-elses would interrupt the graph. There would be like a breakpoint and a fork in a computation graph where computation might need to even return back to CPU and then go back to GPU after the if-else statement was executed. So you kind of want to avoid those in your graph so that your graph can fully operate in GPU only. So once those are fixed, we already went down to, so we fixed those and then did the basic compile and get down to 4.4 seconds. After that, we noticed that we would have different input images from customers coming into the image generation endpoint. So we actually set the range of the tensor sizes that the model would support on the input, and told that to the compiler. So the compiler would be able to handle dynamic shapes on input. So that shaved off some more seconds from the inference time. So now we're down from 7 to 4 seconds. Next, we went down to FP8. The quality decreased a little, and we experiment with different applications of FP8. So to the weights, to the activations, and so the activations would be would be higher precision, and the weights would be lower precision, and then kind of finally both the weights and activations would be at FP8. So I don't know which one we chose finally, but after benchmarking for quality, we chose one of them, and cut down the total inference time by a factor of more than 2 without any perceptible changes on the customer side. And then we compared those results from some of the work from a community, and we saw similar kind of speed ups or even more. So here the speed up is from 6.4 to 3.8, 3.2, and our speed up was slightly larger factor. And another way to speed things up is actually to throw more GPUs in parallel. So you can run in kind of a tensor parallel mode for inference. So if you have one GPU, your inference time would be 5 seconds. If you double the GPUs, you don't double the latency, but you almost double. So you have like a 1.67x speed up. So your cost per output actually is not twice, it's only just 1.2, because you can just in parallel run more stuff through. So you at sort of small increases in cost, but doubling and quadrupling your amount of GPUs handling each image generation, you can actually get significant speed ups at acceptable increases in cost. So right now we are we have an AI team of 4 people. We are participating in multiple initiatives, including speeding up multi-head attention, different attention kernels. So obviously taking inspiration from DeepSeek and their MLA innovations, actively working together with SGLang community. We sponsored hardware for them for running. So SGLang is the fastest LLM engine for running models such as DeepSeek. So it's currently from open source models, it's the state of the art in terms of LLM inference for these, again, state of the art models. So we are collaborating with this team. And on power attention, quantum attention, yeah, working with speeding up inference for videos, general attention models, as well as parallelizing inference on multiple GPUs. So these are kind of, yeah, current initiatives that we are happy to also, or at least I can also forward your questions to our AI team if you have specific technical kind of deep dive questions on those. And I'm also super happy to connect with you guys and discuss more and just brainstorm about any kind of inference needs or questions you might have. That's about it. Yeah.